Hello and welcome back. In this video, we'll apply the equations that we've derived for fluid dynamics to one very simple problem to look at and then one problem from your OpenStax textbook. So just to summarize, we are only looking at incompressible fluids here, which are liquids, and the equation of continuity that we derived a couple of videos ago says that the area at one location in a pipe times the fluid speed at that same location is equal to the area at some other part of the pipe times the fluid speed at that point in the pipe as well. And then Bernoulli's equation is the pressure at some location 1 in the pipe plus rho g y1, where y1 is the vertical height at some point 1 in the pipe, plus 1/2 rho v1 squared is equal to the pressure at some second point in the pipe times rho g y2 plus 1/2 rho v2 squared. So these two equations, both written for incompressible fluids. Make a note here, we didn't specifically point this out in our derivation, but notice that the units for area times speed, what are they? So area has units of meters squared, and speed has units of meters per second. So the collection of units then is going to be meters cubed per second. This is a volume flow rate. This is the rate at which volume flows. Notice this is volume divided by time. The book uses the symbol Q for volume flow rate. So we will use the symbol Q as we look at 1223. So let's look at a pipe that is carrying, let's say, soda water. So soda water or seltzer water has gas bubbles in it, right? So I have drawn these gas bubbles as circles. So here are the circles. And the fluid speed V1 corresponds to this portion of the pipe where the area of the pipe is A1. And then the fluid speed V2 is going to correspond to a narrower part of the pipe where the area is A2. So the question is, what's going to happen to the size of these gas bubbles when they enter this narrower part of the pipe? Are the gas bubbles going to get larger? Are they going to get smaller? Or are they going to stay the size? So at point 2, what happens to gas bubbles? Do they get smaller, larger, or stay the same? Well, remember, gas is compressible. So if the pressure is larger here than it is here at position 1, then the gas bubbles are going to shrink due to that increase in pressure. If instead the pressure is smaller here than at location 1, then the gas bubble is going to expand. If the pressures are the same at location 1 and 2, then the gas bubbles should stay the same. So we want to know what is the pressure relationship between 1 and 2 to be able to answer this question. So we're going to look at these two equations, Bernoulli's equation and the equation of continuity. Notice that we can look at what happens to the fluid speed from the equation of continuity. So from continuity, we know that A1 is greater than A2, therefore V1 is smaller than V2. So the fluid is moving faster in the narrower part of the pipe than it is in the wider part of the pipe. Now we're going to come to Bernoulli's equation. Now Bernoulli. So we're wanting to compare these two pressures right here. Notice that the height of the pipe does not change. So Y1 is equal to Y2. So these two terms will cancel in Bernoulli's equation, and all we'll have is P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. If V1 is smaller than V2, then that means this term is smaller than this term. For this equality to hold, that means the pressures must have opposite relationship. So P1 must be greater than P2. So the pressure here in the wider part of the pipe is larger than the pressure in the smaller part of the pipe. Therefore, gas bubbles expand. So the gas bubbles will become larger in this narrower part of the pipe than they were in the wider part of the pipe. I like to draw an analogy between like a traffic accident or construction where the lanes are merging, maybe 3 lanes into one. So imagine that you have construction going on in these 2 lanes, and your traffic is coming in, and you're waiting, and you're waiting, and you're moving very slow as everybody's filing into this narrow section or this one lane. And so as you're waiting, pressure is increasing, right? You're late for your meeting, or you need to go and do something, or your car is hot, you want to just get out of your car, whatever. Your pressure is large here. You're also moving slow. When you get into that one lane of traffic, things now are moving quickly. You are now feeling better. The pressure is sort of tapered off because now you're actually moving. You're getting to where you're going. So it's kind of, interesting to draw that analogy, but we see that we can get that relationship by using these 2 equations for fluid dynamics that we are going to be considering this semester. Now let's look at one of the problems from your textbook. This is 1223, which reads, what is the pressure drop due to Bernoulli effect as water goes into a 3 centimeter diameter nozzle from a 9 centimeter diameter fire hose while carrying a flow of 40 liters per second? To what maximum height above the nozzle can this water rise? So we're starting off with the diameter of the pipe being 9 centimeters. So that's going to be our position 1. And then it's tapering down to a 3 centimeter diameter pipe. So there are the diameters. We're not told anything about the heights, and actually we're kind of stuck unless we assume that the height's the same. So in other words, the nozzle, this is the picture basically, right? The nozzle and the wider part of the pipe are all have the same center of mass height. So Y1 is equal to Y2. And we want to know what is the pressure change, what experience does the fluid feel with respect to pressure. So let's go ahead and look at A using Bernoulli's equation. So we're going to be looking at P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. And you say, what happened to the other term? Well, I canceled these rho G Y1 and rho G Y2 terms because, again, Y1 is equal to Y2, and so those two terms disappear. So we want to get P2 minus P1. So if I rearrange this equation to solve for P2 minus P1, getting this on one side and everything else on the other, then what I'm going to have is 1/2 rho V1 squared minus 1/2 rho V2 squared. So this is the equation that I want to solve for, and notice that I don't know V1 and V2. So I need another equation to solve for V1 or V2, and of course that's going to come from the equation of continuity. We know the volume flow rate. We're given the volume flow rate, which, recall, I pointed out that that gets the symbol Q as 40 liters per second. In addition, I went and looked up the conversion factor to get from liters to meters cubed. And so we have the volume flow rate. So we know the product of A1, V1, and we know the product of A2, V2. So we can solve for V1 and V2 using volume flow rate. So Q is going to be equal to A1 V1, and so V1 is going to be equal to Q divided by A1. So solving this, Q is 40.0 liters per second, and again we want to convert that. So let's go ahead and multiply. 1 liter is the same as 10 to the minus 3 meters cubed, and then we're going to divide this by the area of the pipe. The area of the pipe is a circle, so this is going to be pi times r squared. R is going to be half of this value, and I'm going to convert that to meters right away, so this is going to be 0.04500 meters, and I got to square that. So this is R1, right? That's R1. Radius 1. Okay, and when we plug in these numbers, what do we get for V1? Okay, so we get 6.29 meters per second. And now we're going to do the same thing for V2. So Q is equal to A2 V2. So I can solve for V2 as Q divided by A2. So this is going to be our 40.0 liters per second. And then again, we need our conversion ratio. 10 to the minus 3 meters cubed is the same as 1 liter. And then we're going to divide this by the area of the pipe. And the area of the pipe is pi times R2 squared. And R2 is going to be 1.5 centimeters. And converting that to meters, 0.01500 meters, and we got to square that. So this is our R2, and now plugging in those values, we get 56.6 meters per second. So 56.6 meters per second. So now we have V1 and V2. Lastly, we need to look up rho. And if you look up rho from the textbook, you'll find for water, rho is 1,000 kilograms per meter cubed. And so now taking our equation P2 minus P1, we can write then P2 minus P1 is equal to, notice that the 1/2 rho is in common for both of those terms, so let's pull it out. 1/2 rho is 1,000 kilograms per meter cubed. And now we're going to multiply by V1 squared minus V2 squared, which is what's going to be left in the parentheses. So V1 is our 6.29 meters per second. We're going to square that, and now we're going to subtract our V2, and that's going to be the 56.6 meters per second, and we're going to square that, close parentheses, and popping that into the calculator, we come up with a drop in pressure of 1.58 times 10 to the 6th. 1.58, and this is a drop, so this is negative, times 10 to the 6th pascals. All right, So this gives us an idea of how to look at a very simple example, which is a soda bottle turned on its side with fluid flowing from the wider part of the bottle to the narrower part of the bottle. We see that the gas bubbles expand because we use the equation of continuity and Bernoulli's equation to analyze what happens to the pressure as the fluid moves from point 1 to point 2. And we have this compressible fluid, which is the gas bubbles in here. And then we applied Bernoulli's equation to 1223 and also coupled it with the equation of continuity, in that the area times the volume does give us the flow rate, which we were given in the problem statement. And so we started off with Bernoulli's equation. We rearranged for what we wanted. We realized we didn't have the velocities, so we went to the volume flow rates, and knowing the areas, we were able to solve for the velocities, and then we came back to Bernoulli's equation and plugged values in, and we see the drop in the pressure. The last part of this problem asks us to find how high up the fluid will move in a gravitational field once it is released from the actual nozzle itself. And this is just conservation of mechanical energy, because once the fluid has left the nozzle, the only force acting on it is the gravitational force. So that means whatever mechanical energy it has just when it leaves the nozzle is going to be equal to the mechanical energy it has up at the top. This is, of course, ignoring air resistance. You must ignore air resistance or else you can't solve this problem. And so it's a very simple case of just setting the kinetic energy that it has when it leaves the nozzle equal to the potential energy it has when it reaches the top. So for part B of this problem of number 23, part B, it's just 1/2 mv2 squared. The velocity at point 2 is the velocity it has when it actually leaves the nozzle, and we can set that equal to mgh, and the masses cancel, and you see h then is just equal to v2 squared over g. And when we take v2, we square it, and we divide it by g, by 2g. I missed my factor of 2 there, excuse me. And so when we plug those values in, we get 163 meters. So you see it shoots up 163 meters, but that's not really how high it's going to shoot up because of air resistance. So here we ignored air resistance, but this is just a example of how we apply conservation of mechanical energy that we've been looking at since about chapter 7. So I hope this gives you a good idea of how to apply the fluid dynamic equations, and we will work more on it in class. We'll see you next time. Thank you.